Now, I'm delighted to welcome Shandu Lainty and Elizabeth Brown from the Manufacturing Technology Center, MTC Research and Technology Organization, to talk about sorting technologies for recycling. Shandu Lainty is Chief Engineer at MTC, helping UK manufacturing adopt new technologies for competitive advantage, while Elizabeth Brown is a Senior Research Engineer within MTC's Technology Transformation Team, supporting industry with identifying, selecting, and adopting impactful manufacturing technologies.
Hi everyone. I'd like to start by saying thank you to UKFT and the ACT Consortium for inviting the MTC to the ACT project and inviting us to speak today. I'd also like to say thank you to Innovate UK for funding the project. It's great to be here today. The fashion industry and I go back a long way. My mother used to work for Frank Usher in the 1970s, and their business model was couture off the peg. And you could say that they were actually pioneers in the fast fashion business. We're here today to talk about how we can turn fast fashion into circular fashion by turning non-rewearables back into yarn and textiles to create circular fashion and textile products. So, after the 2007-2008 financial market collapse and the faster economic recovery of countries with a stronger manufacturing base, the UK government realised it couldn't solely rely on the financial sector, and it needed to invest more in manufacturing. And as part of that, they created the High Value Manufacturing Catapult, which the MTC is a part of. The MTC is a research and technology organisation focused on creating value through the acceleration and adoption of manufacturing technologies. And we are based in Coventry. Just in case anybody doesn't know where Coventry is. But we also have a training centre in Oxford, and we have an office in Liverpool. The MTC has, so the High Value Manufacturing Catapult has 7 partners. Many of these will actually predate the High Value Manufacturing Catapult, such as the AMRC in Sheffield, CPI, which is the old ICI group, and, but the MTC and National Composite Centre were actually created as part of the Catapult. So the MTC has a broad church of capabilities, and engineers from our transformation team, our advanced production systems team, and our digital engineering team all contributed to the UKFT ACT project. So at the MTC, we believe that real tangible value is created when you grow a thing, you mine it, or you manufacture it. And we're lucky enough to work across multiple sectors, including agri-food, mining, and a variety of product manufacturers, as well as the recycling and waste management sector. Our members include household brands such as Rolls-Royce and Unilever, who, through our Technology Advisory Board, keep us focused on what matters to industry. So I'm going to hand you over now to Elizabeth, who has been front and centre of the work carried out by the MTC on behalf of the UKFT and the ACT project, and she's going to tell you a lot more about the technical detail.
Thank you, Shan. Hi, I'm Elizabeth Brown, Senior Research Engineer at MTC. And before I joined the MTC earlier in my career, I was a design engineer for a safety and survival equipment company. I remember quite well, it was about 10 years ago, I went out to visit one of our suppliers who were manufacturing a sub-assembly component for one of our protective suits. They were a small business based in the north of England, and I went out to see them, and the owner took me around, showed me their production facility, took me around the factory and showed me how they did everything. And this material they were using was expensive stuff, and I was just a young, inquisitive design engineer, and I remember asking the owner, what do you do with all your offcuts? Can you recycle them or anything? And the owner said to me, well, in theory, I could get some machinery and I could grind all the offcuts down and then they could be repurposed into something else, but honestly, it's just way too much hassle and expense for me to deal with. I'm just a small business. I've got enough on my plate trying to get my orders out on time and pay my bills. I don't have the bandwidth to mess with any of that, but it's a nice idea. So, okay, I thought. And I didn't appreciate it at the time how that one anecdote would be so representative of the challenge facing our industry towards implementing textile recycling at scale. And now, as Shan just said, at MTC, we focus on supporting UK manufacturing challenges, and particularly those that we call a wicked or a messy problem. So really multifaceted societal problems that need complex analysis to get to solutions. And as we've heard from all the speakers today, I think that tackling textile waste certainly fits the description of a wicked problem. So for this ACT project, MTC, we carried out an initial agnostic assessment of existing technology for an automated sorting and pre-processing facility. And we looked at the gaps and the challenges in the individual areas, which I'm going to touch on. We also looked at emerging technologies that are currently being developed and could be useful for an automated facility in the future. And now we're carrying out trials with some of these technologies to support the development of them, but more importantly, to de-risk them. So business who want to implement technologies like this in future to support textile recycling can do so with greater assurance. So one of the first challenges with automated sorting is the accuracy in fiber identification. Now, there's already sophisticated sensing and sorting technology being used around the world in recycling centers. And this can be applied to sorting textiles. But as we all know, there's specific challenges with textiles that make them difficult, particularly post-consumer garments. One example is the presence of core-spun yarns. Now, these give our clothing all sorts of performance benefits, but in cases where they're really tightly spun, this can make it difficult to detect them with industry standard near-infrared or NIR sensors. Also, certain dyes. So for example, those that use carbon black pigment. These absorb so much light in the visible spectrum, but also in the near-infrared spectrum. So they're not identified as easily using these NIR sensors, so they'll get assigned to an other or an unknown category. And then another quite obvious challenge, as you can imagine, is identifying when there's multiple layers of fibers in a garment. So a jacket like I'm wearing now. And at the moment, these types of complicated multi-layer garments, they have to be manually pre-sorted out so that they don't get misidentified in an automated system and end up going to the incorrect recycling stream where all the different layers would present a problem in the downstream process. Then the technology challenge that in essence affects all the other sorting technologies is the movement and singulation of individual textile items so they can be presented to sorting sensors one at a time. So taking bulk textiles that have been really tightly packed in bales and then spreading them out along conveyors so they're not overlapping and can be presented at speed. Even when, say, robotic arms are employed to pick up textiles and move them from one place to another, it's quite easy for the robot to accidentally pick up more than one or to miss one or to drop an item. It's the same way when you're doing your laundry at home and you got a big pile of clothes and say a sock falls out and you go to retrieve it and then something else falls out. Well, robots have the same issues, especially when you're dealing with post-consumer garments that are unpredictable. They're all different weights, they're all different thicknesses. And so in recent years, sensor technology combined with machine learning has really advanced, and it has the capability to detect and to categorize items in just milliseconds. But the biggest factor limiting the speed of that automated sorting, it's still how reliably and efficiently you can singulate the individual items. So at MTC, we've been doing some trials with different types of fiber identification technologies. I won't go into too much detail about the differences between each one, but essentially these operate by measuring how much light is absorbed and reflected at different wavelengths. Then these measurements can be interpreted to provide an analysis of the molecular composition. And then that data can, in essence, be taught to an AI-based system which can identify fiber compositions and blends in textiles. Now, the three types shown here, they offer different benefits for different use cases, and they come at very different price points. But one of the biggest barriers with assessing the different technologies available is that they've all been developed by different companies with their own, oftentimes, proprietary data sets. So take, for example, if you have a 65-35 cotton polyester blend. If that were to come in incorrectly labeled as, say, 75-25, and that was used to train a machine learning model, well, then that incorrect teaching of what that fiber blend's wavelength absorption looked like, that would skew all the future AI-based interpretations of those results, and they would all be inaccurate. So when technology providers give assurances that their systems have accuracy within certain percentages, that's based off testing against their own data sets or their own textile material libraries. And understandably, some technology providers have developed their libraries and their systems to be focused on quite niche fiber compositions or those that are most prevalent in our consumer waste today. But there's a lack of a standard baseline source of truth textile material database. And by that I mean the fiber composition's been independently verified with chemical or optical testing. So there's no gray area, no doubt about what the fiber composition is. And then for that source of truth data set to be used to objectively test and compare the accuracy of the different systems available. So that's one area where we're doing some trials. Now, as I said before, even with the most sophisticated fiber ID technologies available, they're only as efficient and as fast as the speed and the accuracy that the individual textile items can be presented to the sensors. Now, a great example of this being done is outside the textile industry. This is a materials recycling facility in Coventry. And you can see in this clip, they're using robot arms with vacuum or air suction grippers. And they can remove materials and sort them into different streams as they come down the conveyor at really quite a high speed. But you can probably imagine what happens when you take this, what's really effective technology, these vacuum grippers, for dry mix recycling and try and use them sorting textile waste. Well, surprise, surprise. Porous textile items are not getting picked up. They're not moving anywhere. So at MTC, we carried out some trials with other gripper types to see what can most reliably pick up, random textiles, unpredictable textiles, and pick them up from a pile and move them to a designated location. So we looked at an industry standard 2-finger gripper and also an electric needle gripper. Overall, the electric needle gripper performed the best. It had the least occurrences of double pick, so picking up more than one item at a time. And it was also better with picking up lighter, flimsier textile items than the 2-finger gripper. Now, it does have some limitations because it does pierce through the textile, causing puncture holes, so it's probably not going to be a solution for moving around materials during manufacture or moving reusable materials around a facility. But it's got some real advantage for moving non-reusable textiles accurately and quickly when they've already been destined for recycling streams. Now, taking these technological challenges and opportunities one step further, what if there was a way to get around the need for having to place a textile item up to or underneath the sensor for it to be identified? And that's what UK company Matoa are working on. They offer a range of plastic and textile identification scanners. They have a desktop, a bench-mounted, like in the image there, and handheld units. And they've created a scaled demonstrator integrating their NIR sensor into a robotic arm and gripper. So items can be picked up, identified, and then placed into a designated bin in a single automated action without the need for human involvement. And now Matoa are developing a full-size gripper with their integrated sensor, and they're working together with us at MTC to configure and test this system on industrial speed robots. And what's particularly exciting about this development is that it can be scaled up or down as needed. So rather than having to invest in a really large footprint, high upfront cost automated sorting line, a local sorter could invest in perhaps just one or two sorting robots to handle their non-reusable textiles. Or a system like this could augment an existing automated facility and be designated to handle maybe difficult use case fiber compositions. Now, a crucial step in pre-processing of recycled textile feedstock is disruptor detection and removal. So what is a disruptor? Well, we found that it depends who you ask. The most obvious are physical disruptors, so non-textile trims and hard points, like metal zippers, buttons, and sequins. But there's any number of other features in post-consumer garments that can disrupt a downstream recycling process. So certain types of dyes. Several recyclers shared with us that PVC prints in particular were a problem for their recycling process. Even things like labels and threads, if they're made from a different fiber composition to the rest of the garment, that can cause a problem in certain types of recycling processes. And there are some automated solutions existing already which can separate particularly the heavy physical disruptors from the rest of the textiles. But a lot of these solutions grind up the textiles quite finely in order to be able to do this, that it results in the outputs which get recovered being quite short fiber lengths, which limits the possibilities for recycling. So many companies that we spoke to shared with us that this current state of having to manually remove disruptors and trims from textile items is one of the biggest barriers to be able to process feedstock in an economically feasible way, particularly here in the UK. Now, at last year's conference, Professor Stephen Russell shared that sorting is critical to get the right feed streams to be fed to the right recycling processes. And that's so we can create the maximum commercial value out of our textile waste. But identifying what the right recycling process is for a certain waste stream is one of the biggest challenges to address to ensure that the right technology is implemented to enable the feedstock to be created for that process. So in the same way that different recycling processes are affected differently by disruptors and contaminants, the physical input format, or the actual size of feedstock, is also affected by the downstream process. So some mechanical recyclers want as large as possible swatches or entire garments because they need to carefully preserve the fiber length. Whereas other enzyme-based or chemical recyclers may roughly or finely shred up their textiles before putting through their recycling process. And we interviewed textile recyclers of all types at varying degrees of maturity. Some had been established for decades, others were startups looking for funding. And all of their feedstock needs varied considerably. Currently, many of these recyclers are carrying out their own pre-processing out of necessity, because that is the only way they can ensure that it's right for their processes. But in the future, an automated sorting and pre-processing facility that's utilizing the right technology can support recyclers and help brands and sorters earn money from their textile waste by sorting and pre-processing to the market needs, but crucially at scale.
So, the recyclers and the sorters need your help. As the brand owners and retailers, we need you to demand recycled content in textiles. If the demand is created, the technology, the supply chains, and the price will follow, and together we can make fashion aspirational and sustainable. As Dr. John Parkinson, who'll be speaking later today, said, we call it waste, but it isn't really. It's a raw material. Its potential is only limited by our skill and imagination. Thank you.